Hi all, this is Dr. Labesh Kumar from Department of Mechanical Engineering, Institute of Aeronautical Engineering. So we have already been very much involved in finite element analysis, and last videos also we have discussed about the different ways how to solve a two-dimensional problem. Now today's topic, what I am going to discuss, is related to beams. So beams are very different when compared to our bar problems or two-dimensional shift problems. Now, what we are going to discuss in the beams means how the structural beam will be there and what type of loading will be carried out on a beam element, and what are the particular applications related to the beam element. So, a beam is a structural member in which a system of external loads are acted perpendicular to the axis where bending takes place in the form of deformation. So this is called as a beam. So generally the load is applied in the form of perpendicular loads. So if I mean to say, it will be in the form of like this. Now if I act any load perpendicular to the axis of the beam, now my beam will get deformation in this format. So these elements are called as beam elements. So beam elements are most common type of structural components which are useful in civil and mechanical engineering. So generally a beam is like a structural member whose primary function is to support transverse loading and carry it to the supportives. So we have seen these beams in general construction of a building where two vertical columns will be supported over a beam. So this is called as a beam. So this is an example for how what is a beam. So beams are slender members that are used for supporting transverse loading. So generally it is a long horizontal member in a buildings and bridges where shafts supported in the bearings are some of the examples for a beam. So complex structures with rigid connected members are called as frames and may be founded in automobile and aeroplane structures which has motion and force transmitting mechanisms and machines is an example for this beam element. So generally, if I compare a bar and beam, the two-dimensional equations can be written in the format of d by dx of EAX into du by dx plus q of x. If the differential equation where I compare with the bar and a beam element, now the beam element is d to the power of 4, v by dx to the power of 4 plus q of x is equals to 0. So the order of equation is 2. And here it is a 4. Now, displacement will be in terms of axial displacement in the bar, whereas in a beam we have transverse displacement as well as rotational displacement. That is nothing but slope, we can call it as. So, secondary variable is strain du by dx or stress du by dx. Here we have d square v by dx square d cube v by dx cube. So generally the geometry boundary condition associated with u will be m minus 1 is equals to 0. Here v and du by dx. So natural frequency or natural force or dynamic order will be du by dx of m is 1. Here it is d square v by dx square which is equals to m by ei. Our beam equation we are going to follow to resolve the problems for beam structural beams. Now, a beam is a straight bar element. This is primarily subject to transfer load, assuming that the beam is symmetric about y and z. So I can say that I is equals to, that is I yz is equals to 0. The deformed shape of the beam is described in the transverse direction. So when I describe it, it will be in the transverse direction. Slope will be in the rotational direction. So the transverse displacement and rotational at each end of the beam element are treated as unknown degrees of freedom. That means my beam will undergo two different types of load. One is transverse displacement, the other one is rotational displacement. So for a beam of length L carrying in XY plane, or I mean to say which is in XY plane, has 4 degrees of freedom in a local XY coordinates. So at each node, I will have 2 degrees of freedom. One is in transfer direction, the other one is in rotational direction. Thereby, the equation for or I can say the displacement value for the beam I can given as Q1, Q2, Q3, Q4. If it is 2 noded element. Now note that the counterclockwise rotational degrees of freedom is considered as positive. So wherever the beam, so we have the secondary degree of freedom with respect to slope. Thus, that rotational part, if it is a counterclockwise, we are going to consider it as a positive. So rotation as per the vector point along the z-axis. So along the z-axis. Now, if I want to write a cubic displacement equation, I will write in the form of a1 plus a2x plus a3 x square plus a4 x cube. So now this equation is a 4-noded displacement equation. So now if you see, this is the surface of the beam. So generally one side when it is bending, it will undergo compression. The other side it will undergo tensile or tension. So the neutral surface will be along the axis of the beam. So a beam resists the transverse loading mainly through bending action. So such bendings are produces compressive longitudinal stress in one directional and I mean to say one side. The other side it will be tensile stresses. In order both will be having an impact on the beam. The two regions are separated with respect to a neutral line that is called where the stress will be equal to 0. The combination of tensile and compressive stresses produces an internal bending moment. So whatever when the load is acting on a beam, it will generally produces compressive as well as tensile forces. So such forces will be internally. This movement provides the primary mechanism of the transpose loads of a supporting bar. Okay, generally these beams will have more resistance when the load is applied. Now, one-dimensional mathematical models of the structural beams are constructed on the basis of beam theories. Generally, Euler's theories are used to define this one-dimensional structural elements. The simplest and best known models for straight prismatic beams are Euler theory type. So, Timoshenko is the other beam element where we learn about the beam theory. So, additional importance in beam dynamics and vibrations can be studied in this course. So, both models can be used to formulate beam finite element. One is classical beam theory or engineering beam theory. This is also called as Euler's Bernoulli's theory. And the other one is Timoshenko beam theory. So, the Timoshenko beam theory makes additional importance for beam dynamics and vibration part. Now, Hermite beams elements which neglect transverse shear deformation, but the Timoshenko beams will have the order of correction in transverse shear beam. Now, we will assume that a classical beam is considered. So, the classical beam has a planar symmetry. The longitudinal axis is straight and the cross section of the beam has a longitudinal plane of symmetry. The resultant of the transverse load acting on each section lies on this plane. So, plane symmetry is generally has a cross section of the beam which lies acting on the plane. That means the load acting on each section of the plane lies on this plane. Now, cross-sectional variation will be either consistent or it varies smoothly. Constantly it will be on the part or it will be very smoothly. So, normality, strain energy, linearization, elastic behavior. So, these are the 4 categories on which we will discuss about the bending of the beam. So, the plane section originally normal to the longitudinal axis of the beam remains plane and normal. So, now if I assume this as a plane, so on a longitudinal axis related to beam, we have 2 different portions in the beam. So, remains in the plane and normal to the deformed longitudinal axis. So, longitudinal axis, this will be the deformed portion after application of load. Now, the strain energy, the internal strain energy of the beam member accounts only for bending moment deformation. So all other efforts, notably transverse shears and the axial force effects are ignored. Generally, the axial force which are been present over the beam element will be ignored. Now, the linearization, the transverse deflection, rotational and deformation are considered so small that the assumption of infinitism as well as deformation will be neglected, or sometimes it will be neglected and sometimes it will be considered. It depends upon the consideration of beam theory. The beam is fabricated of a material assumed to be elastic and isentropic. So, elastic and isentropic in a sense, the part beam is very elastic in nature, where the formation of the body will get back into its position after reconsideration of the loads. So, in general, a beam is such an element where it will take transverse loading and also rotational loading. So, when I apply load on the beam, so generally the beam will bend with respect to this format. So, this is the neutral axis along the beam element. Now, above this longitudinal axis, this beam will undergo two types of stresses. Area under this part will undergo, generally, it will undergo bending nature. The other part will be tensile nature. So, bending nature means it will be under compressive part. The second part will be in the tensile part. So, when we have both mechanical properties, then this beam should be considered for deriving the equation for a stiffness matrix. So, generally, if you want to derive the stiffness matrix related to beam, so we need to understand that at each element, the degrees of freedom related, I mean to say, whenever we apply the load, it will undergo into compression and tension. That is nothing but tensile. So, if I draw a FEN diagram for a beam, so we have two nodes. These two nodes will undergo two types of deformation. One is transverse direction deformation. The other one is rotational direction. Similarly, at the other end also we have transverse direction, we have rotational direction. So, counterclockwise is considered to be positive. Otherwise, the rest of the things will be considered negative in this format. So, these loads, now if I want to derive K matrix, that is stiffness matrix for this beam, so generally I will consider with respect to 2 degrees of freedom at each node. At each node, 2 degrees of freedom, one is with respect to transverse direction, the other one is with respect to rotational direction. So, these two will make the beam element to be solved with respect to stiffness matrix. So, generally, if I want to have an equation related to at each part, so I will go with Q1, Q2 at one node and Q3, Q4 at other node. So, when I apply the equations with respect to this Timchenko theory or Euler's beam theory, so finally I will have the strain equations with respect to beam element will be in the form of d square v by dx square, and the other slope form will be d cube by dx cube. So, these are the two equations which we need to follow when we are solving the beam element with respect to the stiffness matrix. So, that's all. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.